Welcome to this week's first lecture in EE557. In the last lecture, we have seen the linear Gaussian systems and how to optimally control them when we have complete information about the state. So from this point on, we are going to start the topic of partial information or control based on partial information. In that case, we are not going to be able to measure the state exactly anymore, but we are going to measure only the outputs which are related to the states, and we are going to learn how to control the systems by using this type of partial information. So when we have partial information, the first task that we have to achieve is to calculate an estimate of the state or the posterior distribution of the state when the measurements are given. Today we are going to start learning about how to calculate the posterior distribution of state given the measurements. So let us write estimation for stochastic dynamic systems. For stochastic dynamic systems, dynamical systems. So I will first start writing the system description. So that is what we all know. So we have xk plus 1 is equal to f of xk, uk, and wk. That is the state equation. And we don't have yk is equal to xk in this case, but we have yk is equal to what we measure is equal to a function of the state, h of xk, and the measurement noise. Okay? And here, this x0 is distributed with an initial distribution px0, and the process noise wk is distributed with some distribution p of wk, and vk is distributed as pvk, the measurement noise. All right? So here I have to talk about what uk is in this case. So we either have uk is either deterministic, so it is known beforehand, so we know the input before we actually start using the system, or uk is a function gk of y0k. So then in the second case we have the closed loop case. First case is the open loop case, and the second case is the closed loop case. And in that case, the input is a function of the current and the previous outputs. All right? So now we would like to achieve or we would like to apply some estimation on the system. So we would like to estimate in some way the state of the system based on those outputs. We see that yk is not equal to xk exactly. So we have a measurement noise plus we have a function there, and that means that we have partial information in this case. We don't have the exact state information, and that means that we need to make some effort to be able to calculate the state or an estimate of the state or the posterior distribution of the state from these outputs. So here we have again our usual assumption, x0, w0, w1, and v0, v1. The basic random variables are independent. Okay. So now I would like to obtain a pictorial representation of this procedure here. So I would have the state equation here. And I know that the input enters the state equation, uk, and the process noise enters the state equation. And we know that the state gets outside the state equation. And then we have the output equation, or let us say the output equation. In that case, we have the measurement noise entering into the output equation, and we have the output state entering, and the output yk is getting out. Okay? So now we really do not know what happens inside this rectangle here. This is the representation of our system, or stochastic dynamical system, and we are not able to measure, or we are not able to reach what this process noise or this measurement noise. We don't know them, but we can know what we know about this system might be the input of the system and the outputs of the system. All the previous outputs and the current output and all of the previous inputs. So here we are going to design an algorithm or design a system that gets this input and this output, and it calculates an estimate of the state. Okay? So we are going to call this system as an observer, or sometimes we can call it state estimator. Okay? And this observer or state estimator is an algorithm that takes the outputs and the inputs of the system, and then that calculates an estimate of the state. Here, what can be an estimate of the state? So, for example, this can be a vector with the same size as the state of the system, and I can show it as xk hat. This type of estimate, which is a vector, and it's a direct estimate of the state, is called a point estimate of the state. So we just estimate the state xk, and that we are done. That is called a point estimate of the state. We only estimate a single point in the state space. Okay? It is not going to be what we are going to do in this course and in this lecture. In this course, what we need to do is to actually obtain the complete information given by the inputs and the outputs about the state xk. And a single point in state space is usually not the complete information. Of course, if the density is not if the posterior density is not an impulse, then a point, just an impulse distribution, is just specified by where it is, a single point. And a single point in general will not be able to summarize the whole information about the state given by these inputs and the outputs. Okay? So we are not going to obtain, or in the way we can obtain such a thing, but this is not going to be our aim here. So we are not aiming to obtain only a single point estimate in this course. Okay? What we would like to do is, instead of a point estimate, we would like to calculate, we would like this observer to calculate the posterior distribution of the state given all of the current and the previous measurements. Okay? This is actually, this density function, this PDF, represents the complete information given by the inputs and the outputs about the state xk. Okay? There is no further information than this. I cannot add anything more about the state into the output of this observer. This type of density estimation, so rather than obtaining a point estimation, making a point estimation, here making density estimation is called in the literature as Bayesian estimation. Bayesian. In this case, I can here put state because we are estimating the posterior distribution of the state. Bayesian state estimation. Okay? So we are not obtaining a point estimate, but we are obtaining a posterior distribution of the state given all of the available information. We are obtaining a density at the end of this procedure. Okay? So here maybe I would like to first explain why I condition this state only on the outputs, because I'm measuring the inputs as well. So here the reasons are as follows. In general, if UK is deterministic, then that means that we know the inputs beforehand. dependent. Okay, we are in this case, if UK is deterministic, we are in this case considering the open loop control. Okay, and in that case, UK is known. Because it's not a stochastic quantity, then I do not write it into this density, into the conditioning of this density function. Okay, but actually I can add those inputs as well here. Okay, so this y0k, if the input is deterministic, is at the same time pxk given y0k and u0k minus 1. Okay? Instead of this, I can write this thing equivalently. Okay? Because in this case, UK is deterministic, and that means that we have open loop control and we know the input beforehand, and I can add here any deterministic and known quantity into the conditioning. Here, for the sake of brevity, I do not add them into this conditioning here. Okay? For the input deterministic case. What about if UK is a function of all of the previous current and the previous outputs? In that case, here, xk, y0k, this y0k in this distribution is already given. Okay, so whatever is in the conditioning of distribution, we know those quantities. Okay, so really here it really doesn't matter if I add this known input into the conditioning again. It won't provide me any additional information. Okay, so this is at the same time equal to xk, y0k, u0k minus 1. Okay. Because these outputs are already known, I know all of the inputs between 0 to k minus 1. Okay? If I know these functions, okay? If I know these functions, if the outputs are known, then I know all of the inputs from time 0 to time k minus 1. What about time k? Why do I not add here input time k? If UK is deterministic, then I can make this u0 to k as well. And here, if this uk is a known function of y0k, then I can add here uk as well. Why do I not add it? Because here, in this system, the fx of uk starts appearing first in the state xk plus 1. And here, I'm calculating the posterior distribution of the state xk. Only the inputs between 0 and k minus 1 determines xk. And xk, in this case, is a function of which variables? I know that it's a function of u0 to k minus 1, and it's a function of w0 to k minus 1, and it's a function of x0. Okay? So here, I can add uk as well if gk is known, but it's not really, it's not going to provide me any more information about xk, because xk is only a function of these variables. Okay, so here I do not add the UK. There is also another reason that I am not adding UK there. The first reason is that it doesn't provide us any information about the state, and the second reason is that I would like to choose this function GK at time k based on this posterior distribution. Okay. So at time k, when we close the loop, if we try to close the loop here, we are going to calculate the input at time k based on this posterior distribution. So that means that the calculation of UK is going to necessitate that I know this PDF. If I add here UK, although it is not it is ineffective in this it doesn't have any effect in this distribution, it is going to mean that for calculating this distribution, I need to know UK, but in order to know UK, I need to know this distribution. It's going to result in a circular dependence, which is what we don't want here, okay? So here, I could continue from this point on by using this distribution, but here I'm just going to summarize this distribution as this one, because all of the information related to U0 k minus 1 is already inside the quantities Y0 k. Okay, so I'm not going to use the given inputs in the given condition. Okay. So I already told you that this type of estimating the density instead of a point estimate here is called Bayesian state estimation. So then why do we not apply Bayesian state estimation all the time? The reason is because it is usually, most of the time, quite computationally and storage-wise prohibitive. Why is that? Because in Bayesian state estimation, we are no longer trying to calculate a vector estimate. We are trying to calculate the density function of a vector, okay? And the density function, in general, is an infinite dimensional quantity, okay? It's a function in a function space. That means that this Bayesian state estimation problem is actually an infinite dimensional estimation problem. It requires infinite dimensional storage facilities, which means that it is impossible, and it requires integrals of functions which are infinite dimensional operations. Okay, so here there are really conceptual difficulties about Bayesian state estimation, which most of the time would make Bayesian state estimation, computationally or storage-wise, exact Bayesian estimation, computational or storage-wise, prohibitive. Okay? So, but here we are going to consider two cases, okay, two specific cases of this estimation problem, in which case the infinite dimensional estimation problem is reduced into a finite dimensional estimation problem. And those two cases, as you might guess here, are the case of finite state Markov chains and the case of linear Gaussian systems. In the case of finite state Markov chains, we know that our density functions are just horizontal vectors with as many elements as the number of states that we can have. And in that case, for the finite state systems, the Bayesian state estimation problem can be done exactly. And similarly, for linear Gaussian systems, we are going to see that these distributions are going to turn out to be Gaussian distributions, which can be parameterized by their mean and covariance, which means that instead of calculating these distributions, I can just calculate a mean and the covariance. And that is going to reduce the infinite dimensional Bayesian state estimation problem into a finite dimensional estimation problem, because we are only required to store and update the mean and the covariance of the distribution, which means that we are only required to store and update finite dimensional quantities, which is going to be exactly possible. And the algorithm that would make it possible is going to be called the Kalman filter. Okay? But in this first lecture, we are first going to see what exact Bayesian state estimation, how it can be done for this general nonlinear system. Okay? So what we are going to derive today is going to be computationally or storage-wise prohibitive in general, but we are going to apply this theory to two specific systems, in which case it's going to be possible to implement this, and we are going to see how estimation is done in both cases. So let us write the Bayesian PDF recursions. So as I told you, we are required to calculate this posterior distribution of the state. And we know that state evolves in time. xk plus 1, xk plus 2. So at each time step, we need to calculate such a density. Okay? And because state is recursive, then we would like to achieve the calculation of this distribution recursively. Okay? That is why, in general, we are going to find a recursion for these posterior distribution functions. Okay? For these PDFs, we are going to find a recursion. In general, it's going to be an infinite dimensional recursion because we are obtaining functions recursively. All right? So from a function, we're going to obtain another function. The next density, the density of the next state. Okay? So in order to be able to achieve such a recursion, I'm going to calculate two distributions. Okay? Pxk given y0k. This is called the estimated PDF. Estimated PDF. And this is the PDF of xk given all of the current and the past measurements. Okay? This is the PDF of xk given all of the current and the past measurements. And in general, we can abbreviate this distribution as follows. Pk given k of xk by skipping the conditioning here. Okay? The second distribution, which we are going to base our recursion on, is given as follows. Pxk plus 1 given y0k. Okay? So in this case, we are given all of the measurements between time 0 and time k, and we are going to predict the next state. We are going to predict the distribution of the next state. Okay? So this is called the predicted PDF. Predicted posterior state distribution, estimated posterior state distribution. Okay? And we can abbreviate this as pk plus 1 given k, the PDF of xk plus 1 given all of the measurements between between time 0 and time k. This is PDF of xk plus 1. So we have the following figure. So I have the time k minus 1 here, okay? So I would have here k minus 2, k minus 3. So if I would like to calculate the state at time k, given all of the measurements between 0 and k, in estimation theory, this is called filtering, okay? You are trying to estimate a quantity at time k given all of the information between time 0 and k is included. Okay? This is called filtering in the literature. So sometimes instead of estimated PDF, we say filtered PDF. Okay? Filtered PDF. So if we would like to estimate a quantity in the future, given the information between time 0 and k, we are calling this operation as prediction. All right? And sometimes, we are not going to do it in this course, but sometimes we are required to calculate the estimate of a quantity in the past, given all of the information between 0 and k. Okay? And this is called, in the estimation literature, as smoothing operation. Okay? But in this course, we are only going to be interested in filtering and prediction, because we are going to see that this Bayesian PDF recursion is going to be composed of two parts. The first part is going to be related to estimation, and the second part is going to be related to the prediction. operation. Okay? So, but you need to be aware of this type of terminology. So if you are trying to estimate a current quantity, given all of the current and the past information, this is called filtering. If you are trying to estimate something in the future, given the same information, this is called prediction. If you are trying to estimate something in the past, given the current and the past information, we are calling this as smoothing. Okay? So now I'm going to form a recursion for these posterior distributions. Okay? The first thing that I can do, but I will not choose this way actually. So let me write this. So I can first calculate, let me see how I write this. So I have Pxk given y0k. What we are going to do is that from this distribution, we can try to obtain Pxk plus 1 given y0k plus 1. Okay? This is definitely a recursion. So I make k's here, k plus 1 here. Okay? So this is the next iterate of this quantity. Okay? Usually, the Bayesian PDF recursion is given in 2 steps. So I generally do not directly write this as a function of this PDF. Okay? Instead, I put another distribution into the middle. Okay? And that distribution becomes xk plus 1 given y0k. Okay? So what is this? What is this distribution? And this is a predicted PDF, and these two are estimated or filtered PDFs. Okay? So going from this distribution to that distribution is called a time update. Time update or a prediction update. This is the name of this operation, going from this PDF to this PDF. So what are we doing here? We are keeping the given information the same, but we go from time k to time k plus 1. So with the same information, we just propagate time of the state vector that we estimate. Okay? So that is why this is called a time update or a prediction update. And the second step, going from this distribution to that distribution, is called a measurement update. Or sometimes it is called a correction. Okay? There are different names. So in that case, what we are doing is that we are keeping the time of the quantity that we are trying to calculate the distribution of the same. So both of the distributions are with respect to xk plus 1, but we increase the amount of information in the given condition. So into this given information, we add yk plus 1. So here, I have the additional information of yk plus 1. Given, and when I combine this distribution with this additional information, I don't know how to combine them yet, but I obtain just this new distribution. Okay? So this recursion, therefore, is divided into 2 parts as time update and the measurement update. And in both, if I can do both of these steps, then I know how to obtain this distribution from this distribution. Okay? So I can here say that this time update is only going to be related to the state equation. Why? Because from the state equation we learn how to go from time, how state goes from time k to time k plus 1. Okay? And this measurement update, because it is related to the inclusion of this measurement in the given condition, is related to the measurement equation or output equation. Okay? So as a result, the Bayesian recursion that we are going to learn is going to combine the information of these two information sources. These equations are kind of information sources for us. The first information source, the state equation, gives us how the state propagates in time. And the second source of information, the output equation, tells us how measurements are related to the states. So this Bayesian recursion combines the information in these two information sources. All right? So now, instead of establishing a recursion like that, I'm going to just shift this recursion just a little bit. So instead of first using this one, I will first calculate the predicted distribution, y0. It really doesn't matter from which distribution that you start, but in our investigation, it's going to be more meaningful to start from this distribution. We are going to see why in the initialization of this Bayesian recursion. From this one, I will add the measurement yk, and I will obtain the estimated PDF or the filtered PDF. And from this one, I will make a time update to obtain xk plus 1 given y0k. So I have the same recursion here, but I just shifted my phase. I look at this recursion from here, this one, and this one. Okay? So here, let us try to characterize these updates. From this distribution to this distribution, I have xk. These are related to xk both, so time doesn't change, but the amount of information changes. And there is a new information here, and it is yk. So this is a measurement update, or a correction. And this is a time update, because the information remains the same, but the time of the quantities that we are trying to calculate the PDF of changes. So this is time update. Okay? So now let us start building our recursion. So for obtaining a recursion for these distributions, what I need to have first is an initial condition. I need to initialize the distributions first. So let us see how we can initialize. So I will first initialize. So this is going to be the form of my recursion, and I will first initialize this quantity by setting k equals to 0. So initialization. In this case, I'm setting k equals to 0, okay? And in that case, this would be px0 given y0 minus 1, okay? In general, this is a predicted PDF, okay? And what I need to calculate here, a distribution of x0 given all of the measurements in the past, not the current measurement, but the measurements in the past, okay? Look at this. xk given y0k minus 1. If we are at time k is equal to 0, our first measurement is y0, coming at time k equals to 0. But here what I would like to do is to look at the measurements. These are y0 to minus 1, okay? What are the previous measurements for time k equals to 0? I know that this should be empty set because we really do not have any measurements in the past, okay? So here, this given condition here, it's just an empty set. Nothing is given to us. For the predicted distribution, I don't have any given information at time 0. Okay? So this is going to be px0 itself. Okay? So at time 0, we have no past measurements. That means that I shouldn't have any given condition here, which means that this y0 to minus 1 should be an empty set, and that means that the first predicted distribution for time k is equal to 0 should be equal to the p of x0, which is given to us in the problem. Okay? So here, the initialization for our recursion is that p0 given minus 1 of x0 is equal to p of x0. Okay? So we initialize our recursion here at time k equals to 0 with the prior information about the state x0. All right? Because there is no information for the predicted distribution at time k equals to 0. So then what should I do? From the predicted distribution, I need to make a measurement update and I need to calculate the estimated distribution. Okay? So what I need to do is to calculate from p0 to minus 1, I need to use y0 here, and I need to calculate p0 given 0. Okay? This is going to be a measurement update. Okay? So now let us consider the measurement update. Correction. This is sometimes called correction. The meaning of correction is that in this update, we predict something which might be quite erroneous, and then we use the measurement to correct that prediction. Okay? So that is why the measurement update is sometimes called correction. So in the measurement update, what we would like to do is to calculate, given pk given k minus 1, we need to calculate pk given k. Okay? That is what measurement update should do. Let me write these distributions. I have pxk given y0 k minus 1. From this distribution, I need to use the measurement yk to calculate this distribution, pxk given y0k. So I need to incorporate this information given by the measurement yk into this predicted distribution to calculate this updated or corrected this distribution or estimated this distribution. Okay? So I'm going to start from this one, this distribution, and by using the probability rules, I'm going to try to write this distribution in terms of this predicted distribution. Okay? Let us try to do that. In this case, you need to be very, very familiar with the probability rules that we discussed at the beginning of the semester. Okay? This conditioning, the adding something into the condition, extracting something from the conditioning, etc., or the total probability theorem. You need to be very, very familiar in order to be able to understand these parts. So let me start with the updated distribution here, or estimated distribution. This is equal to, I can remove this conditioning by writing the conditional probability rule here, pxk y0k divided by py0k. Okay? And then I'm going to separate the effect of yk from this block of information. So instead of this, I will write the following. I have xk. I will separate yk from here. Yk, and I have y0k minus 1. And I will do the same for the denominator. Yk, and I have y0k minus 1. All right? Then I'm going to write this distribution using the conditioning rules as follows. Yk given the other quantities, xk, y0k minus 1, and p, xk, y0k minus 1. In this case, you have to remember that this conditioning distribution, by using a conditioning rule like this, is nothing but this one divided by this distribution. Okay? That is why this joint distribution is the multiplication of this conditional distribution times the conditions here. Okay? Divided by, I will do the same in the denominator. So I will have pyk given y0 k minus 1 and py0 k minus 1. Okay? So here, what is this division? I divide the joint distribution by the marginal distribution of y0 to k minus 1. What is this division? By this type of conditioning rule, I know that this is pxk given y0 k minus 1. Okay? I know that this is xk given y0 k minus 1, which is our predicted distribution. What we are trying to do here is that we are trying to write this distribution in terms of this one. So you see that I started with this distribution, and I at the end obtained this distribution here, which is this one. Okay. So what about the other terms? Let us try to summarize the other terms. So here the other terms are going to be simplified somehow. So here we are looking at the distribution of yk given xk. Xk is given to us. Okay? In this equation, we are trying to calculate the distribution of yk given the value of xk. Xk is given to us. Okay? So the only term for randomness here is vk. And I know that this vk, the measurement noise, is independent of the past. Okay? Given xk, the randomness or the distribution of yk is only dependent on the measurement noise vk. And vk is independent of the past measurements. So actually I can remove this term from this first term. Okay? So then if I continue here, that is going to be equal to, let me write, pxk y0k is going to be pyk given xk. I removed the past measurements because I'm repeating here myself. So here, given xk, the only randomness about yk is provided by the measurement noise vk. And vk is independent of all of the past measurements. Past measurements, past inputs, past states. It's all independent of all of those quantities. Okay? So I would have I will replace this ratio with this one. So pxk given y0 k minus 1 divided by pyk given y0 k minus 1. So here, because xk is not in the given conditions here, I cannot remove this term. Because the previous measurements would of course provide information about yk, okay? The current measurement. So I cannot remove this one because xk is not in the given conditions. If xk is in the given conditions, then these past measurements would not provide any information for the current measurement, because all of the memory of the system is related to this state variable. All of the memory in the measurements is coming from the states. Okay? So if I give the state in the given condition, then I do not have to provide the earlier measurements. But if in the given condition I am not given the state, then I cannot remove the past measurements, because definitely past measurements, when the state is not given to us, would give us some information about the current measurement via the state. Okay? So here this is one of the formulas that we are going to use. But here you see that this distribution is a distribution of xk, and xk is here and xk is here. But in the denominator there is no xk. So we might actually guess that this term in the denominator is nothing but a normalization constant. Okay? So now I'm going to try to prove that this denominator here is nothing but the normalization constant of this multiplication. Okay? So when I multiply a distribution with the likelihood function here, the resulting multiplication, the integral of it with respect to xk does not have to be equal to 1. Okay? That is why this constant comes here. That constant is actually the constant that normalizes the integral of this quantity to 1. Why should that integral be 1? Because this distribution, when I integrate this distribution on the left with respect to xk, I need to obtain 1. Okay? That is why we need to normalize this multiplication with a constant to make the integral of the resulting ratio with respect to xk exactly equal to 1. Okay? So now let me concentrate on this denominator. P yk given y0 k minus 1. Now here I would like to write this distribution in terms of these numerator quantities. Okay? But you see that in none of the terms, either in the conditioning, neither in the conditioning nor in the actual argument of the distribution, I don't have xk. So why not just add xk into the argument of this distribution? So I use the total probability theorem here to add xk into the argument of this distribution. So this is total probability theorem. And we see that the joint distribution, when I integrate with respect to xk, the resulting thing should be the marginal conditional distribution. Okay? So now I can apply my conditioning rules on this joint distribution. Okay? That is going to be P yk. I will pass this xk to the given condition. Okay? xk y0 k minus 1. And I need to multiply this with pxk given y0 k minus 1. Okay? dxk. So you can actually try to obtain this type of rule because of the following conditioning rule. Pyk xk y0 k minus 1. This is nothing but this joint distribution pyk xk given y0 k minus 1 divided by pxk given y0 k minus 1. In the conditioning rule, you can add any conditions, and here the common condition is y0 to k minus 1, and you can write this type of relationship by using the conditioning theorem or conditioning rule with this common additional condition here, and then this joint distribution is nothing but the multiplication of this one times this one. That is what I did here. All right? But here you see that what is in the integral is nothing but the numerator here. I can remove these terms here because xk is given. I can remove these past measurements from here, and that would give me p yk given y0 k minus 1. This is the predictive measurement PDF, and it is the integral of the numerator here. pyk given xk, pxk given y0 k minus 1 dxk. Okay? So we see that the denominator here is nothing but the normalization constant of the numerator. Okay? So now let me write the final formula. Pxk given y0k is equal to pyk given xk, the likelihood, times the predicted distribution, xk given y0 k minus 1, divided by this integral of the numerator. dxk. So I know that this is pk given k, and this is pk given k minus 1. So I can write my rule as, this is the correction or the measurement update rule, pk given k xk is equal to the likelihood Pyk given xk times the predicted distribution pk given k minus 1 xk divided by the integral of the numerator. Pyk given xk, pk given k minus 1 xk dxk. So we know that in the correction or the measurement update, what we are doing is that we are adding the information of the current measurement into this predicted distribution. Okay? In this predicted distribution, the information of yk does not exist. Okay? When we combine the information of yk with this predicted distribution, we obtain the estimated distribution or the filtered distribution. Okay? This equation tells us how to incorporate the additional information of yk into the predicted distribution. Okay? What we are doing in order to be able to add that information is that I multiply the predicted distribution with the likelihood. I know what yk is. I know the value of yk here. I substitute it here, and I consider this likelihood as a function of xk. Okay? I have the predicted distribution, pk given k minus 1, and I have also another function, p of yk given xk. So this is p of yk given xk. This is xk. Yk is fixed at our measurement. Whatever measurement we collect, we fix yk there, and we look at the likelihood as a function of xk. Okay? So this likelihood term, this likelihood as a function of xk, contains the information related to yk about xk. We multiply this predicted distribution and we multiply this likelihood function. So incorporation of the information of yk into the predicted distribution is done by the multiplication of two functions. So multiply the likelihood with the prior information, which is the predicted distribution. Okay? So this is nothing but the base rule, actually. All right? So the incorporation of new information according to Bayesian rules happens in terms of a multiplication in the density domain. We multiply the prior distribution, which is the predicted distribution here, with the likelihood. And when we multiply, so this is the multiplication. So in that case, this predicted distribution approaches a little bit to the likelihood, okay? But the resulting quantity, this multiplication, usually does not integrate to 1. So this multiplication is not a density function with respect to xk in general, okay? That is why we need to normalize it. So first multiply, then normalize. That is how the incorporation of the information of new measurement is done into the density domain. All right? So this was the correction or the measurement update. And what about this likelihood? How can I calculate this likelihood? At the beginning of this course, in the first 2 or 3 weeks, we have learned about how to calculate this likelihood. And we know that it can be calculated by using the measurement equation. Okay? So the correction or the measurement update is only related to the measurement equation. The time update is going to be related to the state equation. So this update here is the incorporation of the information of the measurement plus the measurement equation into the posterior densities. All right? So that completes our investigation of the measurement update. Now we're ready for the time update. So I have time or prediction update. So in the prediction update, what we have to do is to start with this estimated PDF, okay? We're going to start with pk given k of xk, and then we are going to increase the time index of the state. So we're going to obtain pk plus 1 given k of xk plus 1, okay? And we're going to keep the information the same. We see that in both of the cases, I have the information from y0 to yk. So we are not going to be adding any new information into the distribution, but we are propagating the state, okay? But that is done with the state equation. I know the distribution of the current state, and I am going to use the density information of the process noise to propagate the next time instant. All right? In general, correction or measurement update brings new information into the density. And in general, the prediction update makes us lose information. Okay? Because in the correction or the measurement update, we are adding the information of yk into our distribution. But in the time update or the prediction update, we don't add any new information. Instead, we are trying to propagate time. But because of the process noise, that prediction is going to be erroneous somehow. Okay? It's going to contain errors. That means that we are going to lose information in the density domain when we try to make the time update. So in correction, in measurement update, we gain information, and in time update, we lose information. So Bayesian recursion, it contains just both of these terms. In one of them, you gain information. In the second one, you lose information, and you combine this. It would be nice if in the overall you gain some information about the state. So now let us write the distributions here. P of xk given y0k. From this one, I'm going to calculate pxk plus 1 given y0k. Okay? You see that no new information comes, but I just propagate time from k to k plus 1. All right? So now let us try to do that. I will start with this distribution, and I will try to write this distribution in terms of this one again. So let me write the predicted distribution, xk plus 1 given y0k. Here I do not want to make any change in the given condition, but I need to bring xk into the picture. If I need to bring additional variables into the picture, I always use total probability theorem. Here, when I try to write this thing in terms of the numerator, I needed to bring the xk into the picture. Okay? That is why I use the total probability theorem to add into the arguments xk. Here I am going to do the same thing. This is integral, this is total probability theorem. P of xk plus 1, I need to bring the new random variable xk here, y0k dxk. Okay? And then I'm going to apply the same rule that I applied here. I want to put xk into the conditioning. Okay? I want to bring xk into the conditioning, and I'm going to use this type of rule there. That is equal to, once you start doing this type of probability manipulations, it becomes automatic. Okay? If I want to pass this xk to here, I know that first I need to write this xk plus 1, and I would pass this xk here, y0k, and then the second term is always going to be this xk conditioned on this original conditioning. Okay? xk given y0k dxk. But you can always write this conditioning type of rules there too. So here this distribution is nothing but this joint distribution divided by this marginal distribution, marginal conditional distribution and joint conditional distribution. So here you see that this is my pk given k. Okay, that is good. And this is my pk plus 1 given k. So I have already obtained pk plus 1 given k on the left, and I'm trying to write it in terms of pk given k. Okay, that's good. The only thing that I need to manipulate here a little bit is this conditional distribution. Okay, and it is going to be interesting to do that manipulation. So here, let me consider that PDF in the given condition. xk plus 1 given xk, and I have y0k. Okay. So now what I would like to do here is to write the distribution of xk plus 1 given xk. Xk is already given to us, and we are trying to write the distribution of xk plus 1. Okay? So this thing is given, and we are trying to write the distribution of this one. So there are two unknowns here, uk and wk. xk is given to us. So here I will consider, so I know that the input uk is either deterministic, open loop, known, or it is stochastic, closed loop, g of y0k. Okay? Let me consider both of these cases. So first of all, if uk is deterministic, in this case I have open loop control, and meaning that uk is known beforehand. Okay? So then what happens? xk is given to us, uk is given to us. In the case of uk is deterministic, xk is given to us, uk is given to us. So the only randomness in xk plus 1 is due to this process noise. And I know that this process noise is independent with all of these measurements. Okay? That process noise is independent with all of the past and the current measurements. Okay? So that means that in this case I can remove this thing here. P of xk plus 1, xk, y0k. I can remove this y0k in the case of deterministic input, known input. Okay? And because I know what uk is, I can add it into the given condition. It really doesn't matter. uk is known, so I can add it into the given condition. So in this case, you see that I could write this like this. So let us say that if uk is equal to gk y0k, if uk is obtained using feedback of the outputs, and in this case, we have uk is random, so we have closed loop operation. Okay? So now let me try to write this expression. Pxk plus 1 given xk y0k. In this case, do you think I can just remove this y0k and write this as p of xk plus 1 given xk? So xk is given in both cases. Xk is given, and there are two unknowns, uk and wk. So what about the other information, this y0k? I know that y0k can be used to determine uk. Okay? If y0k is not given, I don't know uk and I don't know wk. If y0k is not given, then I don't know uk and I don't know wk. Okay? So it's this distribution. And when both of them are known, if xk and y0k are known, I know xk and I know what uk is by this formula. Okay? uk is a deterministic function of y0k, then I know what uk is. So that is why, in this case, I know xk and uk. The only thing that I don't know is wk. But in this case, I know only xk, and nothing is known about uk and wk. Okay? So that is why these two distributions are not equal when uk is random. Okay? I cannot just blindly remove those measurements from the given conditions, because the measurements are providing us information about this unknown uk here, okay, in this equation. So then what to do? How to get rid of that y0k? Here is how to do it. So I have pxk plus 1 given xk y0k. So here, xk is known and y0k is known. I can add here into the given condition anything that can be calculated using these given conditions. Okay? So here, I can actually write xk plus 1 given xk, y0k, and here I can add uk as well. Okay? The addition of uk here doesn't bring us any new information, because I know that from y0k, I can already calculate that uk. So this uk, adding this uk here does not bring us any new information. Okay? So I can do this addition. But when xk and uk are given to us, the only randomness in xk plus 1 is about this process noise. When xk and uk are given to us, the only randomness in xk plus 1 is about the process noise wk. And I know that wk is independent with this y0k. Okay? So in that case, I can remove y0k, pxk plus 1 given xk, and instead of I remove y0k and I just add uk here. Okay? So we see here that in the case of random uk, I can remove this y0k, but I need to add uk here into the given condition. Okay? Because otherwise this uk will be unknown, and it's going to provide additional stochasticity into xk plus 1, which is this case, which I don't want. Okay? But here, when I look at the deterministic, when I look at the open loop case, when I look at the closed loop case, I have the same distribution. Okay? So then I can replace this distribution in the integral with that one, with this one. Okay? So now let us try to add that. So I have pxk plus 1 given y0k is equal to integral pxk plus 1 given xk uk, and and I have p of xk y0k dxk. So this is my formula. I have a form of one-step transition distribution here, and I have the estimated distribution, and I have the predicted distribution that I would like to calculate. Okay? So now if I would like to write this as a rule in terms of pk given k and pk plus 1 given k, I can write the prediction as follows. pk plus 1 given k of xk plus 1 is nothing but integral pxk plus 1 given xk uk times pk given k xk dxk. Okay? So this is the time update, general time update formula in the Bayesian recursion. Okay? And what about this one-step transition PDF? It is required in order to be able to make this time update in the density domain. It can be calculated by using the state equation. So we see that the time update is related to the state equation, and the measurement update is related to the measurement equation. Okay? So when we look at this type of formula, it is not definitely exactly clear what this operation is going to look like. The measurement update is multiplication and then normalization. What about this thing? If you think about this, you are actually going to see that this operation, time update operation in general, is a form of convolution. Okay? So when we have a predicted distribution like this, usually this type of multiplication and integral is a form of convolution, meaning that this distribution is going to get a larger variance in general when we apply this type of time update operation. Okay? So in density domain, incorporation of measurements is multiplication. Bayes rule it is. And the time domain, propagation of time is convolution. So when I have these distributions, so this is the estimated distribution. Let me say pk minus 1 given k minus 1. Then we predict this. Usually what happens is that when we apply a time update to an estimated PDF, usually what happens is that mean changes a little bit. I'm considering Gaussians here. Mean changes a little bit and the variance increases. Why is the variance increasing? Because of the process noise. We have the density of the state, but we have the uncertainty of the process noise. And this addition of this process noise brings us some uncertainty. That is why when we go from pk minus 1 to k, let me say this one, this is pk given k. When we go into pk plus 1 given k, what happens is that this distribution becomes more uncertain. Okay, so the variance is enlarged in that case, and the mean can change according to the dynamics of the state. And when the measurement k plus 1 comes, suppose that I have suppose that I have the similar measurement. Suppose that I have the equation xk plus vk. This is my measurement equation, and suppose that this is my yk. In that case, the likelihood would look like this. Suppose that the measurement noise is small, the likelihood would look like this type of distribution. So this is p yk plus 1 given xk plus 1. Okay? So this is my likelihood, this is my actual measurement. It can be anywhere in this state space, and this is my likelihood. Then what we do in the measurement update to incorporate this measurement information of yk plus 1 is that we multiply the predicted distribution with the likelihood. Okay? And if your measurement noise is small, then this large covariance or large variance distribution approaches a little bit to the measurement, and its variance gets smaller. Okay? So I would get a distribution like this, and this becomes pk plus 1 given k plus 1. So in measurement update, the uncertainty, entropy, or variance, however you measure uncertainty, that gets smaller. Okay? And in prediction update, the uncertainty becomes larger due to the process noise. This is because in measurement update, we are adding information in the density domain, and in prediction update, we are propagating time, which increases uncertainty due to the process noise. Okay? So So these are the Bayesian recursions. You see that in the density domain, you have to take some integrals, you have to multiply some functions. Okay? And in order to be able to do this operation, you have to actually store these functions, pk given k minus 1, and you have to take multidimensional probably integrals here. That is why implementing the actual Bayesian recursions are very difficult, if not impossible. Okay? So we cannot actually implement these density formulas exactly in reality. Only in some specific cases. In some specific cases, we are going to see that these operations would turn into operations in finite domain, on finite domain quantities. In finite state Markov chains, the density functions are going to be vectors. Okay? And in that case, these integrals would turn into summations with finite number of operations. And in that case, we will be able to do these operations exactly. Because in finite state Markov chains, we have discrete random variables, meaning that these summations would turn into, these integrals would turn into summations. And in linear Gaussian systems, all of these densities, pk given kxk, pk plus 1 given kxk plus 1, they would turn out to be Gaussian distributions. And that means that instead of applying these operations, I can try to apply equivalent operations on the mean and the covariance of the distributions. And that means that I do not have to deal with continuous density functions. I would have to deal with only a mean and the covariance. And the recursions we would find for the mean and the covariance, instead of these density functions, would be called Kalman filter. And in general, if you have a nonlinear system and non-Gaussian system, exact calculation of this recursion would be impossible. And in that case, we have different methodologies, different approximation methodologies. For example, if you have a nonlinear system, then a methodology in order to be able to apply a Kalman filter-like idea to that system might be linearization. And if you apply linearization to the system, and if you apply Kalman filter on the resulting linearization, the resulting algorithm is called extended Kalman filter. There are other types of linearizations which I will not be able to talk about, but for general nonlinear systems, for general measurement nonlinearities, we have something called Monte Carlo methods or sequential Monte Carlo methods. And instead of approximating the model, instead of linearization on this model, such methods try to approximate these distributions as impulse mixtures. And if you have impulse mixtures, which are called particle mixtures, in that case, storing these densities and taking these integrals will turn into easy operations. And those type of state estimation methods are called particle filters, or they are called, the general umbrella is called sequential Monte Carlo methods. And the Monte Carlo comes from the representation of this density. So instead of approximating this transition distribution, and instead of approximating this likelihood, which is done by linearization in general, we are approximating these distributions instead. We are keeping this transition and the likelihood the same, but we approximate the state distributions using particles, and those methods are called particle filters or sequential Monte Carlo methods. But we are not going to enter those topics in this course. So that is going to be all for this lecture. In the next lecture, we're going to apply these Bayesian recursions onto finite state Markov chains. That's all for this one. Thank you for watching. Bye.